getting into this first problem here, how do you think through the problem? So my first recommendation is always completely read it. The reason I have these what are called context-rich problems is because that's the way reality presents itself to us. We don't have math book problems in real life. You have to think a little bit deeper than that. And so you have to read it slowly, read the whole thing, and then zero in on what I'm going to call the big pictures. And the biggest picture is what information is the container. It holds everything in the problem. And then what is it that you're looking for? And so in this first part, so this is a trip where you drop one group of people off at one spot where they can just float downstream without paddling. Then you go 10 miles downstream and let off the rest of the folks who are going to paddle upstream because they want to work out, I guess. And you know that they're going to meet in the middle, and you have knowledge about how fast they go, so you want to figure out where to meet them, so that because you're bringing lunch, you're bringing the beer, or whatever it is you're doing. And so how do you zero in on what the big picture is? And so if you come to this middle sentence here, the second pair will begin at the same time as the first from 10 miles downstream. So I guess we're on the phone or something. So 10 miles, the biggest part of this picture is that I have point A, which I'll just put a line in the sand here, and I have point B, and the distance between these two things, point A and B, is 10 miles. That's the big picture that contains everything in this system. The system consists of a river and two boats heading towards one another at different speeds. Okay, so this diagram container constrains the whole picture of our thoughts here. And so that's one kind of first level thing. And then what you're looking for, where will you wait? So there's some spot X, and whether you draw it right in the middle or not doesn't really matter much, okay? It's up to you where you put it. And I'm gonna actually do that. I'm gonna put it in the middle. You know it probably isn't in the middle. It's probably a little bit off center in reality, but the diagram isn't the diagram isn't the answer. Diagram helps me get an answer. All right. So I'm using these colors, and in fact, when class is over today, magically, right above this celebration of knowledge, there'll be a PDF of what I'm scribbling on screen. And then this video will be available in Blackboard as well. So I've now found the big picture container of A to B, and I know what I'm looking for. I'm looking for this position X. It'll be some number of miles away from A, and a different 10 minus that away from B. All right, so we have that level. Now you start drilling into the details. So two people will put a canoe in the river and just drift downstream at 1.5 miles an hour. So this piece of information, 1.5 miles per hour, they're heading towards this X marks the spot, all right? And that's some distance, okay? So the displacement, we could call it delta X sub A, which is representing the distance between X and A, the displacement from one location to another. And according to the first zeroth law, which you've had lots of video blabbing about, would be V delta T. This is just the first zeroth law in my textbook, and it's just a standard kinematics equation in every other physics textbook. So now we have described the people who are just coasting down the river, okay? And we're modeling, and that's what we do in science. We model things. We build a mathematical model, a diagrammatical model, a graphical model, and we use those things to generate new information until we have the answer that we are looking for, and sometimes we get answers that we weren't looking for. All right, and you know that this other group they'll have an average velocity of 2.5 miles an hour relative to the shore when they go against the river current. So I'm going to call this I'm going to use W just so we don't have our V's confused. It doesn't matter what letter you use for these things as long as you know what it represents. And since it's a speed, it must be some sort of speed or velocity. It's technically a velocity since we know what direction it's going. And so again, delta xb that is going to be the leftover. It's going to be 10 minus x. That's what that length is. 10 minus, oh, by the way, forgot to draw in here. This is assuming that A is at 0 miles, and B is at 10 miles. That's implied in the picture, okay? And since this is a change in position, the first zeroth law says that change in position is always the speed associated with that change in position times the time interval. And this is also just an expanded version of the first zeroth law. And you've seen this in videos. And so now I have two displacements, okay? And they end up being equal, but really all you need to know is that x equals x. You can solve for x, or delta x equals delta x, all right? So that's the setup. That's how I'd use the first zeroth law and encode for this situation. So the blue, green, pink, red, and black, that is the mathematical model, okay, for this situation. And technically speaking, at this point, the physics is done, and it's a math problem from here on out, all right? So that's how you set up the first problem. And these should remain in order. I don't think I set it to have a random order of the problems, but you'll recognize them by their narratives. And all that will change is the numbers. It cycles through a different set of numbers each time, all right? So that's number one. Number two, and half of this test is the exact same big idea, just pitched a different way each time. So it's a lake, it's a circular lake. We pick a circular lake because it's easy to do that. It really wouldn't matter. It could be any length as you'll see. And so you're walking and talking, somebody is running the opposite way and they have an interesting t-shirt, and you're like, okay, I didn't finish reading that because they were going too fast. How long before I see them again? So you want to be paying attention. So that's the short version of this story. And again, what's the big picture? The lake, oops, got stuck in highlighter mode. The lake is 3.4 miles in circumference. So you could just say, all right, circumference 3.4 miles. Now you might think that it matters that it's a circle. All that matters is the length. You could snip that circle and lay it out flat, and it would be just like the boat problem. There is a distance along a line that could be thought of as straight. All right? And so I'm not going to draw a picture. A circle, you might think, oh, pi r squared, 2 pi r. You think you might have to make it more complicated than it is. It isn't, because the motion doesn't necessarily know that you're going in a circle. Time and distance is happening, and it can be modeled in a linear fashion. All right. your walking speed at 3 miles an hour? Well, tell you what, let's make W for walking speed is 3 miles an hour. And the runner's speed is 7 miles an hour. So V equals 7 miles an hour. So we're writing this information down. Now, every textbook in the universe will tell you when you start solving a problem, write down all the knowns, figure out what the unknown is, and look for equations. And one of the reasons that they have you do that is the more information you write down, the less mystery there is. If you try to solve it all at once, we don't do that. It wouldn't be a test. That's why the homework was the way it was: plug and chug and get an answer. So now we've listed all the known information, okay, and now it's time to start modeling. And so it is the case that speed times time, so the runner speed times this time interval will be the runner's displacement. Okay, this is the first zeroth law. Okay, been over that a bit, and technically delta S for the runner would be that. Okay, but we don't need that in this problem. We just need to know that speed times time gives me a distance, and I'm concerned about how far will the runner go. And then this is a little bit less obvious here, but this is the walker's displacement that closes the gap. Okay? Now, I want to be careful here. So, technically, speed times time for the walker speed times time is the walker's displacement. The walker's displacement that closes the gap is the total distance minus what the walker walks. All right? There's no formula for that. That's just thinking about the situation in the same way that we thought about the last problem. And I'm going to do each one of these problems slightly or completely different, even though they're fundamentally the same problem. Okay, they're the same thinking and the same equations. And the reason I'm doing that is even in a group of only 6 people online today, 1 here, 5 online, there's at least 2 different ways of thinking about these things. And one way is more suitable than the other for the individuals. And so you have this. So there's that level of modeling, but there's one last thing to know, is whatever distance the walker travels, which we can model with WT, plus whatever distance the runner travels, which we can model with VT, the sum of those 2 distances, the next time they meet, has to equal the circumference. And so at this point is you want to know how long it'll be. You solve for t. And what you'll find is that it ends up being the case that the 2 displacements have to equal each other. These 2 things have to be equal to one another. That's what you get when you solve this. You can just rearrange it as c minus wt. And so one displacement equals the other when you close the gap. Otherwise, they wouldn't be the same. And that's not entirely obvious to everybody. Some people, they innately know that, and they can do this, or sometimes they need to see the math. So there's probably points in between that help people see how this works. All right. Next problem. This is another straight line problem, but this time the two distances that each person travels are the same. They're literally the same distance. It's from one house to another, as I recall this problem. And so we know right from the beginning that displacement 1, so I'm going to use English and turn it into Mathlish, because we think in English. Very few of us think in math. We need some sort of bridge between that. And so since we're talking about displacement, that means that we're talking about the first zeroth law. It means delta S equals V delta T. Okay? And so let's get at this problem. She runs at a very consistent pace at 3, while your average speed is 4. So there's 2 different speeds, and she's gonna run to the house first and unlock it. Okay, except you notice she drops her keys a few minutes later. And so you gotta figure out what distance to make up here. So we have this situation, and displacement 1, I can write it as V1T, and displacement 2 is going to be V2, but it's going to be T plus that offset. And the offset that I'm talking about, this delta T, is this 5 minutes later piece of the puzzle. And so want to pause and give a moment to process here. Is these 2 displacements are equal because they are absolutely the same distance, and hopefully that's obvious in the statement here. But the person who leaves later, there's a time offset. And normally that delta means, and I also typically would put a delta on all t's, but in this case I wanted to keep that separate so that our offset wouldn't be confused with the same, with what t is. And t is always a time interval. It's always a delta of something. It's not, even if it's 0, but in textbooks they often don't use the deltas as much as they should. That's just a feature of the way this topic is taught, the variety of ways. And so here it'll help us to use the delta just for this offset, okay? And this problem is the one I'm essentially giving you everything but the final solution step, because there's a really subtle part of this puzzle that not everybody would think through. But this beginning step 1, if you will, this displacement equals that displacement. We knew that had to be true, but they're obviously going to be a little bit different in terms of their speed and time, because we're told there's 2 different speeds, and we know that there's an offset of time, so that has to be accounted for mathematically, and that's what this does. Mathematically, we're accounting for this here in this model, okay? Next part. So what I can do is some math now. V1t equals V2t plus V2 delta t. You took algebra for a reason, so that you could do stuff like that in this course. And I know what each speed is. I know V1 is 3 and V2 is 4, and I know that that delta t is a 5 minutes. I don't know what t is. So normally we would just go straight for solving for t. So V1t minus V2t equals V2 delta t, and that means t is V2 delta t over V1 minus V2. Problem is, I don't need to know what T is. What I need to know is how far from your house will you be when you catch up to her if you leave immediately and run at your usual pace. Okay? And so I started this problem, I didn't identify what we were looking for, I just started modeling. So that's another way to go, and I show that in multiple videos that you'll take notes on, ones you have and ones you will. How you start, is one way will be more or less natural than the other way, depending on who you are. All right, so here we get down to something where I don't need to know this time. I could solve for it. All right, and that's one way to go. But then you haven't answered the question, because the question is how far from your house will you be when you catch up, not how long will it take you to get there. So hopefully you know that the distance that we're looking for is going to be V1 times that, which if I just carry that through, now I have my answer. The distance we're looking for will just be this right here. So basically, I've given this problem away. And I wanted to do that because the thinking, there's some parts in there that could stumble you more than the other things, namely what's in green. And so you would solve for a time and you would be like, all right, am I going to put what speed am I going to put with this to get a distance? All right. Next problem. High school athletic, diving. What's the speed when they hit the water? Because we don't want them to get hurt, so to speak. So as I read this problem, the diver moves through the air with a constant acceleration of 9.8. She passes a lower diving board 3 meters above the water. It took 2 seconds to enter the water from the time the diver passed the lower board. Okay, so I have an acceleration. I have a distance. And I have a time. And I know that since the person is moving, there's speed involved. And so this is why we would begin. We were like, you know what? There was a displacement. There was an initial speed and time, and there was an acceleration term. This is the combined zeroth law. We'll talk about the trinket I sent for that and the Desmos way to verify it and compare your math to physics. We know that this combined zeroth law, or the fizzle for first, sizzle for second, and kazil, whatever that is, for this one. So you can solve for V naught given all the inputs, and you'll need to do that to get what you need for part 2 of this solution. And here's the other thing to know, and I'm going to put this out here, but I'm not going to pretend that it's obvious that you would know immediately that you need the zeroth law theorem, which is the ADS equals V bar dV. Okay, and so V bar is 1/2 V plus V naught, and delta V is just V minus V naught. Well, that is the factored form, those two binomials, of a difference of perfect squares, or that, which means ADS equals V bar dV would just be V squared minus v naught squared, or half of that, which means we would write 2ADS equals v bar dv. Now, every physics textbook in the universe will show this equation. I'm sorry. Let me correct that. V squared minus v naught squared. That's what every textbook shows instead of the zeroth law theorem. And it depends on the problem which one is the easiest to use. I give you some where the zeroth law theorem is as I pitch it, the top one there, is the easiest way. And then there's times where this classic one down here is the best tool. It just depends on the problem, all right? So why would I use this thing? Well, I know there's an acceleration, 9.8. I know there's a displacement, okay? And I know that that means that there's a change in speed, and if there's a change in speed, there's an average. And if there's a change in anything, there's an average version of that, period, all the time. So the number of times that the zeroth law theorem is useful is a lot of times, okay? So there's that. And of course, that V naught would be something you could use in this equation as you solve for the final speed that you're looking for, all right? So some things to recall, though, is that the acceleration in this problem is 9.8 meters per second every second, which is the same thing as meters per second squared, but what's a square second? That makes no sense. And we know that h is 3. Oh, but this is little g. So we've had some talk of that recently, and a lot more to come on that. So what I can do is the zeroth law theorem can be updated, okay, from this ADS, 2ADS equals v squared minus v naught squared to be 2GH equals v squared minus v naught squared. How essential is that? Not essential, really, as long as you know that A is 9.8 and delta S is the h that we're talking about. But height is the way the problem was specified, and it's the way you look at it in reality. You would think, oh, the diving board is this high above the water. You wouldn't think, oh, the displacement between the water and the board. Nobody talks like that. Only weird people speak that way. So this kind of brings it closer to reality, closer to the truth of reality in an equation form. Is it necessary? No, absolutely not. But you will see it pitched this way in pretty much every textbook. And so all we would do here is solve for v. You would have generated what v naught was earlier. You can put it in there. These things into there, and you solve for v. Easy peasy. Oh, it's a good thing that I am recording on my iPad. Did I start the recording? Oh, good. It's recorded in 2 places because I wanted to put this on YouTube as well. All right. 4 down, 2 to go. So a skateboard competition, and we'll get deeper into problems like this as we get into force and energy, and it'll get more complicated. But in this one, it's relatively simple. And so basically, you know already some things about this, that the skateboarder typically goes about 95 feet in 6 seconds. That means you can get an average speed, okay? It actually won't matter in this problem how much the skateboarder weighs, how much the skateboard weighs. None of that would matter. The degrees won't even matter for this problem. We're only concerned with the motion and how that changes, not its causes. So kinematics is about motion, and its changes. Dynamics is about why there's kinematics. Would be a short answer. All right, so once again, we can say, you know what? I know that this person's going to hit this ramp at a speed, go up the ramp, and stop the speed. So I know that there's a change in speed, and if there's a change in speed, there's two things. There's an average. There's actually three things. Every change has its own average. A change in speed means acceleration. That's the definition of it. And if you change the speed of something, if it's moving, it has a displacement. So the zeroth law theorem is a nice tool that captures all of those elements. It has everything that we want to know or do know, all bottled up into that. And this one is going to be nice to just leave it in this form. It'll be easier that way. So first I want to unpack this average velocity part. Okay, so average velocity, it ends up being the case if you took the deriving the kinematics equations notes, the graphical analysis stuff, you know that average velocity ends up being what the first zeroth law says. It also is the sum of the endpoints over 2. It's the literal arithmetic average. You could think of this in this case as d over t because we're talking about a straight line distance. And so if the distance traveled is a straight line, it's the same as displacement because displacement's a vector. It's the distance between, straight line distance between 2 points. So you could have a displacement of 0 and a distance that's not. For instance, if I walk from where I'm at to the door and back, that's probably 30 feet total, 15 one way, 15 the other. Displacement 0, distance 30, because it was a straight line back and forth. All right, so make sure you get distance and displacement straight in your mind, and this is definitely computable. You have the distance and the time right there in this problem. Now, delta V. I'm going to, on the handout, I have it off to the right here, but I kind of took too much space there. So velocity and time. All right, so let's and again, this is stuff that we just did in notes that you were supposed to do or have done this week. So here is a graph. You go from an initial velocity to a final velocity. And in this case, the initial velocity is going to be high, it's going to come down, but this is more of just building a particular relationship here. So this right here, this height of the triangle, this is a delta V, all right? And we know that the area under a velocity time graph, again, just from notes, is a displacement. And the reason is the product of the units. The velocity is meters per second, time is seconds, meters per second times seconds is meters. So every time you have a velocity time graph, you have a displacement. So technically, this area, I'm going to change colors here, delta S is going to be 1/2 delta V delta T, because that's a triangle. It's delta V high, it's delta T wide, it's half of a rectangle. That's why its area is a displacement. We'll call it delta S from the first zeroth law. And so that's one thing there. But what's the connection between it and its average? Well, if you look at this right here, in fact, I'm going to if I think about this area, this rectangle area, well, this is half delta V high. So this area in the rectangle, delta S is half delta V high and delta T wide. So these are the same. This right here and this right here are the same thing. So you could sort of almost, if you could snip that triangle and flip it down, you just took off that top chunk of area halfway up on delta V and flipped it down, you have a rectangle. So it's just it's the same displacement, but it's in terms of an average, okay? And this uniform thing. So I'm, depending on you seeing and taking notes on those other things, if you didn't do that yet, well, it'll make more sense when you go back and do it. And so what this basically tells me, okay, is that the change in speed is double the average. So if you think about the zeroth law theorem, okay, you can compute V bar and delta V and then solve for A. You already have delta S. You can immediately grab V bar. You could compute delta V by doubling it, or you could have half delta V. It's whatever floats your boat in that regard. There's two ways to proceed, but the bottom line is you can compute this and that. You already know the delta S, and you can solve for A. Okay, so this formula here just requires two steps to get the right-hand side values, and then you solve it for A and plug in delta S, and you are in business. Now, this last one is a full-on graphical analysis problem, which you have notes to take on that for easy points. And so I want to go back to the first method of where I'm going to have these color-coded things where model it as we go. All right? So this is two cars. You're going a speed. Your friend passes you going at what you believe is a constant speed. You want to catch up because apparently you can't tolerate that person beating you. All right? So you read through all of this stuff, or you can just say you are riding along at a comfortable speed of 20 miles per hour. Okay? Now, here's the thing is there's nothing about the problem the way that it's stated that gives me a big picture constraint like that boat problem did. So when you don't have that, you have to model it as you go. Just build in the information as you go. So I'm gonna take this phrase, this part of a sentence, okay, all right, how would I model that? And so I have a speed. Speed requires time to change position, so I'm gonna draw a graph, a V versus T graph, and I have this 20 miles per hour that's on this graph. And right now, you're riding along at a comfortable speed of 20 miles per hour when you see your friend is going to pass you at what you think to be a constant 30 miles an hour. Okay, so let's draw a VT graph for the friend. Okay, I wasn't looking at the, Wonder if the battery died on this. Yeah, I think I need a better battery. So I'm going to switch to testing 1, 2. Here we go. All right, so can you hear me now? Yeah. Man, those are some lousy batteries. And I just changed them. They must have been dead to begin with, to get a new set. All right. So, let me get this mic a little bit closer. All right. There. Hopefully you weren't going too long in audio silence. All right, so the friend passes at a constant 30. So this one, there's more information. I know that the friend is going 30 miles an hour, and that they're going to do this for some amount of time. Okay, and that time is also something that's going to constrain the motion of the person who wants to catch up and not be forever passed by this person. So here, time sneaks in. Don't know what the time value is. I just know that they're coordinated. These motions are coordinated in time, all right? And so that means if I'm going to accelerate at a constant 20.25 miles per hour, okay, then I know that if I'm increasing acceleration, or my acceleration is positive, I'm going to have an increasing speed. It has to be that way. And now that we're talking about acceleration, we could draw an acceleration graph, 0.25 miles per hour per second, and this is also constrained by that same time. Now here's the deal, is on the pink and the green, I now know stuff. This is a displacement. Area under a velocity time graph is displacement. And so I could call this delta x sub 1, it's going to be v delta t. It's okay. And I know that this acceleration curve, the area under that is a velocity, change in velocity, and that's going to be a delta t. There is no change in velocity for the pink person, the person who just on cruise at 30 miles an hour. All right, but there is going to be a change in velocity, and that also means that we're dealing with a change in displacement. And so there's two parts of the displacement. There's this bottom part that is the initial velocity times the time interval. So there's a chunk of the speed involved with, this is v naught here. And then there's this 1/2 delta v delta t. So that means that the area under this velocity time curve has two parts to it. Call this delta x2, I guess. And it's a v naught delta t plus 1/2 delta v delta t. All right, and so we have this, that's really just that combined zeroth log in, except in delta v terms instead of at squared terms. They're the same thing. And again, you have these two displacements, and you can take, let's see here, this isn't on the notes, but this accelerated at 0.25, that's a value that can go in here, which means delta V, whatever delta V ends up being, can come up and be in that equation. And so this is all showed in those other video notes, okay? But the bottom line is delta x1 equals delta x2, same as before. The first two or three, first 1 to 3 problems, I think, were that way, and now this one is again. And you solve for that in your business. And so there's some math left to do on that problem, and you're good to go.